This is Algebra 2 at Trig. We're doing Unit 5A.2. We're going to apply properties of rational exponents. Properties that we've already learned about in the past are if the bases are the same and we're multiplying the bases, we're going to add the exponents. So if multiplying bases, the same base, you add the exponents. Here, this little square that should be actually a multiplication symbol, we're going to multiply the same base. That means we're going to add this exponents. So we're going to add the 1/2 plus the 1/3. And we know to add fractions, we need common denominators. So the simple part is knowing that the denominator is going to be 6 because 2 and 3 both go into 6. But what are the tops going to be? To get a 2 to become a 6, you got to multiply it by 3. So you got to multiply the top by 3 also. To make the 3 become a 6, I got to multiply it by 2. So I got to multiply the top by 2 also. So that's going to become y to the 5/6. So we add our exponents even if they're fractions. When we're raising a power to the power, we are going to multiply exponents. So in this case, even with rational exponents, rational just means fractional. So this is going to be 1 times 1, which is 1, and 2 times 3, which is 6. So 1/6 as a power. This is a monomial. There is not a plus in between the a and the b. So you can distribute the m through. And that would be a to the m power and b to that same m power. So in this case, we're going to take the 8 to the 1/3 power and x to the 1/3 power. That's going to become 8 to the 1/3 power is the same thing as the cube root. So the cube root of 8 is 2. X to the 1/3 power. You might write that as the cubed root of x. If the question is written with a rational exponent, you should give your answer with a rational exponent. But just so you understand what's happening, the 1/3 just means cubed root. Here we have a negative exponent. That tells us to put the base into the denominator with a positive exponent. So the negative exponent means to put it into the denominator. And because the original question started with a fractional exponent, we should write it with a fractional exponent. But I'll just point out to you, just as a reminder, that when the denominator is that number, that represents the index of your radical. We would write a 2 in that corner. But a square root, which is the 2, typically is not written. So you wouldn't need to write that 2 in there. It's implied that if it's not written, it's automatically a 2. If the bases are the same in a fraction problem, you're going to subtract exponents. So in this case over here, we are going to subtract the bottom exponent from the top exponent. And to do that, we need common denominators. We need 6 as our smallest number that both 2 and 3 go into. If the 2 is going to become a 6, you got to multiply it by 3. If the 3 is going to become a 6, you got to multiply it by 2. So that's going to become y to the 1/6. Here, if it's on the outside of the parentheses, just like earlier, you can distribute that into your fraction. Sometimes that's convenient. It's probably more convenient to go the opposite direction, to pull it out. But occasionally, maybe. So we get x to the 1/3 and 8 to the 1/3. Remember, 8 to the 1/3 is just the cubed root of 8. And we should know the cubed root of 8 is 2. So 8 to the 1/3 power is 2. You can write this as x to the 1/3, or you can write this as the cubed root of x over 2. Because it started with a fractional exponent, we should probably write our answer with a fractional exponent. Here we have a multiplication. Again, the square implies that it didn't process correctly. So, what I notice here is that we're going to be able to break this into 2 separate radicals. So that's what we're going to end up doing here. We're going to look at this as the cubed root of 40 and the cubed root of x to the 5th. Consider them to be separate problems. So 40 can be broken down into 8 times 5. I choose 8 times 5, not 4 times 10. I chose 8 times 5 because I know the cubed root of 8. Now, when we look at the cubed root of x to the 5th, we got a group of 3 of them. That's what a cubed root's looking for. Do you have 3 of a kind? And the answer is yes. So this is going to be 2 cubed root of 5 times x cubed root of x squared, because you have 2 left over. So your final answer should probably be 2x the cubed root of 5x squared. So let's take a look at what we just did there. We only looked at the 40 and then we looked at the x. We broke the 40 apart into something that has a perfect cube in it. We looked at the x to the 5th and saw that we have a cube inside of there also. So we pulled that out to the first power. That's not x cubed. This is x to the first power. It's the cubed root of x squared. So your 2 times x gives you 2x. The cube root of 5 and the cube root of x squared goes inside the radical. Here we could take the radical of the numerator and the radical of the denominator. So we can take the cubed root of x and we can take the cubed root of 8. We know that the cubed root of 8 is 2. Because the question started with a radical, we would write our final answer with a radical. Now to start looking at some examples. This is asking for the cube root of 25. Remember, when we look at our power chart, we can see that under the cube root spot, we get 125 when we're working with 5. So the cube root of 125 is 5. And of course, we know that the cube root of 8 is 2. So this should be 10. Over here, this is a fraction. Notice that this is the fifth root, and it's a fifth root on top and bottom. That means, to make this more simpler for yourself, there's other ways to solve this or evaluate this. But you can write this into one large radical. That becomes 32. And 2 to the 5th power. If you look at the 5th root, we see we have 32. So 32, the 5th root of 32 is 2. So now we're working with the cubed root of 104. You've got to look at what 104 can break down into. This would be 2 times 52. That's 104. Neither of those are perfect cubes. 2 times, and 52 can be broken up into 2 times 26. We have the 2 times 2 times 2 times 13. There's my 3 of a kind that I've been looking for. Cube root's looking for 3 of a kind. But there's not 3 of a kind in 13. You can't factor it apart with 3 of a kind in it. Cube root again. Okay, we look at this, trying to figure out what can break that apart. Well, it's an even number, so I know for sure 2 goes into it. 2 goes into it 216. And wait a minute. 216 is on my power chart under the cube. So the cube root of 216 is 6. You want to be familiar with your power chart. $96 . 3 goes into 9, 3 goes into 6. So 3 goes into that 32 times. And I remember 32 was on my power chart. So the fifth root of 32 is 2. And that's what we're doing. The fifth root of 32 is 2. And then this last one, the fourth root of 2 times 81, because it's an even number, we break it down to the 2. I see 81 there. I remember 81 was on my power chart. The fourth root of 81 is 3. Now, as we look at this last set, down here, we're going to do this tomorrow. We're going to do the variables the second day. So we're just going to finish up with these last 4. So subtraction rules are the way they've always been. You've got to have like terms. And for radicals to be like terms, like radicals, they got to have the same index and the same radicand. So the indexes are both 5s, the radicands are both 12s. So this is really 7 minus 1, x to the 5th. Or, sorry, this is 5 minus 1, which is 6. This is the 5th root of 12. Or this is 7 minus 1, which is 6, and the 5th root of 12. Said it right that time. All right. Looking here, what's going to happen on the test are people are going to add what's called the radicands together. You can't do that. You can't add those together. You've got to get them to be the same before you do any adding. So I need to try to make them the same. I see that this is 3 times 16. I see that this is 3 times 25. Now there's many ways for us to get 48. We could have talked about 2 times 24. 12 times 4, many different ways. But the reason I picked these two factors are because I know the square root of 16. And I know the square root of 25. I want to use some smart factors. I want to use factors that are going to help me with the problem. And since these are square roots, I want to use perfect squares. So 4 plus 5 is 9, root 3. Now, you could test this out with a calculator. You could type in, I'm not asking you to solve these with a calculator. I'm asking you can check your work if you're doing your homework. The square root of 48 and the square root of 75 gives you a crazy decimal, 15.588. Well, 9 root 3 is also 15.588. Same answer. Think about how this would work out. Work through the next two, pause the video, see how you do, come back and I'll finish it up. So we're looking at the cubed root of 81. We've got 3 times 3 times 3 times 3. That makes 81. And 3 times 3. Nope. And 2 times 2 times 2 times 3. We've got the cube root, 3 of a kind. We've got the cube root, 3 of a kind. So we're going to bring out the 3, which gives us the cube root of 3 left over, because a 3 was left over. We pull out the 2. We still have the cube root of 3. So notice the like terms. Notice the radical is exactly the same. So we can do 3 minus 2, which is 1. 1 root 3. That is actually the cube root of 3. 1 cube root of 3. Last one. You might have to work a little bit at trying to figure out how to break these down. But I recognize that this is 5 times 81. This is the 4th root of 16 times 5. I know they have to have something in common. I need the 4th root, so I can go down my 4th root column, and I can look for numbers that can go into the values I'm looking for. 81 can go into 405. 16 can go into 80. Those are perfect 4th roots. So the 4th root of 81 we saw was 3. Cube root of 5, 4th root of 5. Plus the 4th root of 16 is 2. 4th root of 5. So this has to become a 6. 4th root of 5 plus 2, 4th root of 5. 6 plus 2 is 8, and they're both the 4th root of 5.